Hello there. In the last video we talked about how to solve exponential equations, namely equations that had variables, unknown variables, in the exponents of the expressions. So we explored that logarithms were actually the key tool in order to solve exponential equations. Now in this video we're going to sort of flip the script and sort of go backwards. So pretty much how to solve logarithmic equations. And it is going to be based on the following principle. Namely, the inverses of logarithms, or the inverse of logarithmic functions, are exponential functions, right? So what does that mean? So that means, remember, there's a key property that is associated with this particular expression, that is a to the power log base a of x is actually just going to be equal to what? Just x. So we're going to be using this property in this video to solve logarithmic equations, and also bringing up a few of the special properties of logarithms that can make our process a lot easier as well. Alright, so let's begin by starting off with some basic logarithmic equations. So let's consider the natural log of the square root of x plus 2 is equal to 1. Now you may be like, oh, well, that's not really an easy example to start with. Well, actually, it's not as scary as it looks. So remember that square roots are actually the same thing as fractional powers, right? So we can rewrite that expression as so. And then we can use our properties of exponents and bring this 1/2 down. So we have 1/2 times the natural log of x plus 2 is equal to 1. And then we can bring that 1/2 to the other side by multiplying both sides by 2. So we're going to have natural log of x plus 2 is equal to 2. Now the equation doesn't look as scary. So now what I'm going to do is I'm going to focus on getting rid of this logarithm. Remember that the natural log is the same as a log base e. So the inverse of the natural logarithm is of course going to be the natural exponential, which is going to be e. So we're going to exponentiate both sides by e. So that means both sides of the equation become exponents of this new equation. Okay, so what do we have here? So e and natural log cancel, so e to the natural log of something is just equal to something. So we're just going to have x plus 2 is equal to e squared. And then I'm just going to subtract both sides of this equation by 2, and that gives us the solution. So x is going to be equal to -2 plus e squared is the solution to our original equation. Second example, a little bit easy. Suppose we have the natural log of x is equal to -3. So is it possible that the natural log of a number is equal to a negative? Well, remember the range of a logarithmic function is -infinity to infinity. So yes, it is possible. And the value of x must be between 0 and 1. Those are the only values that will return a negative value. So let's see what that number is. So I'm going to begin by exponentiating both sides by e, so they will cancel. And then we're just left with x is equal to e to the -3rd as our solution. Right? Not too bad. All right, so let's make it a little bit more in depth. Suppose we have the natural log of x plus the natural log of x minus 2 is equal to 1. So now we have two instances of x here, so it may become a little bit more complicated. So let's just look a moment here at the possible values of x. So x must be greater than 0 for this first logarithm, and x must be greater than 2 in order for this first logarithm to work, right? So whatever values that we may get in the final solution, they have to satisfy these particular properties. So if x is greater than 2, then x is greater than 0. Therefore, this is going to be our restriction. So this is the restriction for possible x values, right? So if we get a value at the end that's like -6, -6 is not greater than 2, so we're just going to cast that out as a bad solution, okay? So let's just keep that in the back of our mind for a minute. So x must be greater than 2 is our restriction for our possible solutions. And now let us continue how to solve this, right? So remember when we add logarithms, that's the same thing as taking the logarithm of the product of those interiors. So this is actually the same as writing the natural log of x times x minus 2 and that must be equal to 1. And then I'm going to exponentiate both sides by e to get rid of this natural log. And then that's going to give us what? So that's going to give us x times x minus 2 is going to be equal to e to the first, which is just going to be e. I'm going to distribute this x, and that's going to give us a quadratic equation, obviously. So we're going to have x squared minus 2x minus e is equal to 0. So we already know how to solve quadratic equations. So let's just take a look at the discriminant. So the discriminant is going to be b squared minus 4ac. So that's just going to be equal to 4 plus 4e. Not too scary, right? So it's going to be just 4 times 1 plus e. And this is going to be a positive number, right? So since the discriminant is going to be greater than 0, there's going to be 2 solutions associated to this particular quadratic equation. And what are they? All right, so our solutions are going to be of the form x is equal to negative b plus or minus the square root of the discriminant all over 2a, and a is going to be equal to 1. So we have 2 plus or minus the square root of delta, so that's going to be 4 times 1 plus e all over 2. The square root of 4 is 2, and those 2's will cancel, so that's wonderful. So x is going to be equal to 1 plus or minus the square root of 1 plus e. Right? So what do we know actually about the square root of 1 plus e? So the square root of 1 plus e is actually going to be greater than 1. Well, how do I know that? Well, the square root of 1 is going to be 1. Therefore, 1 plus something has a square root that's going to be greater than the square root of the thing for which I'm adding to it, right? So the square root of 1 plus e is going to be greater than 1, and this is going to be important. And I'm going to explain that why in just a moment. So from this expression, we get 2 possible solutions. The first is going to be 1 plus the square root of 1 plus e, and x2 is going to be 1 minus the square root of 1 plus e. Right? So let's analyze these solutions, because we remember we have a restriction on our possible solutions, right? Remember, x must be greater than 2. This must be true. So is any of these numbers, 1 plus the square root of 1 plus e and its opposite, greater than 2? So this number here is greater than 1. Therefore, this number here is greater than 2, right? Because square root of 1 plus e is greater than 1, therefore 1 plus it must be greater than 1 plus 1, which is 2, right? So x1 checks out. What about this number? So the square root of 1 plus e is greater than 1. So when we take a number greater than 1 away from 1, so that's like 1 minus 2, that's going to give us a negative number, right? So x2 must be less than 0, and that's bad. That violates that restriction. So therefore, the only solution that we have, so I'm just going to call that x star, is going to be equal to 1 plus the square root of 1 plus e. So that's the only solution to the original equation that we started with. All right, so let's make these examples a little bit more fun than that, or maybe not. Who knows? It's all subjective. So let's consider the log base 2 of x plus the log base 2 of x plus 2. Let's figure out what value of x makes this equal to the log base 2 of x plus 6. All right, so now we have 3 instances of x's. Now, just a side comment, notice that all of these logarithms are the same exact base. If they're not the same exact base, this problem gets exponentially more difficult to solve, right? So if you have like log base 2, log base 3, and log base 4, that's a little bit more tedious and difficult. But I'm not going to discuss that scenario here. So let's look at the restrictions that we need to apply on our possible values of x. So for the first, we must have x must be greater than 0. The next, x must be greater than negative 2. And the last, x must be greater than negative 6. So we choose the intersection of all of these intervals, which clearly must be x is greater than 0, right? So if we get 1 or 2 or 3, that's perfectly fine. But if we get negative 1, negative 7, then those are going to be out. All right, so let's begin by solving this. So notice we're adding these 2 logs, right? And then we're going to be subtracting this log once we move that to the other side, right? So we can actually write this instead as log base 2 of x plus the log base 2 of x plus 2 minus the log base 2 of x plus 6 is all equal to 0. So when you add logarithms, you multiply their interiors. When you subtract logarithms, you divide their interiors. Therefore, using both of those rules at the same exact time, this is equivalent to writing the log base 2 of x times x plus 2 all over x plus 6 must be equal to 0. Now I'm going to get rid of this logarithm. So the inverse of a log base 2 is going to be an exponent with a base of 2, so I'm going to exponentiate both sides by 2. So I have 2 to the log and 2 to the 0 on the right-hand side. So they cancel by design. And then we have 2 to the 0 on the right-hand side. That's just going to be 1. So I'm going to have x times x plus 2 all over x plus 6 must be equal to 1. Right? So it's a nice equation now. So multiply both sides by x plus 6. We're going to have x times x plus 2 must be equal to x plus 6. Let's distribute. X squared plus 2x is going to be equal to x plus 6. And then isolate and set it equal to 0 since we're in quadratic form. X squared plus x minus 6 is equal to 0. Alright, so we have one of these equations, not too scary. So we can factor that. That's just going to be x plus 3 times x minus 2 must be equal to 0. So that means x must be equal to negative 3, or x must be equal to 2. And remember, we have some restrictions on x. X must be greater than 0. Therefore, we need to cast out this value of negative 3 because the natural log of negative 3 is not in the real plane, right? Therefore, the only solution, I'm going to call x star, is going to be equal to 2. So that's the only solution to the equation of interest. So let's do another example, more fun. Suppose we have the log of 10 over x is going to be equal to 1 minus the log of x. Now, depending on the country and the literature, some people take log as base e, some people take it to base 10. So make sure, if you're taking a class or you're reading a book, make sure this is defined and you're using it for what's defined or intended to be used as. So we're just going to assume that this is going to be a log 10 base, okay? But if it's log base e, then you would do it in a very similar way, of course. Okay. So I'm going to begin by adding log base 10 x to both sides. So I'm going to move him to the left. So that's going to give me the log base 10 of 10 over x plus the log base 10 of x. And those are both going to be equal to 1. So I'm getting my logarithms to the same side. I'm adding two logs, so I'm going to be multiplying their interiors together. So that's going to be the log base 10 of 10 over x times x must be equal to 1. And notice here, x cannot be equal to 0, right? So 0 is bad. And we need to keep that in mind here. X must be not equal to 0, and also, if we look at this particular logarithm, we have a restriction. X must be greater than 0, right? So we take the intersection of those two restrictions, so that means that is the restriction we need to keep in mind, right? Because notice here, x disappears, right? And we get that the log base 10 of 10 is equal to 1. Notice that all our x's disappeared, and this is a true statement. So usually we say, when we have a true statement when we're solving an equation, we say all real numbers. That's usually what we say, except those for which are less than or equal to 0, right? So therefore, what is our solution? So that means our solution is any value x in the interval 0 to infinity, and some people usually abbreviate this simply as the positive reals. So that's the solution to that equation. All right, so let's just do one more example just to make sure we understand, because this pretty much brings together a lot of different components, right, from different parts of pre-calc. So let's solve the equation, the natural log of 5 plus the natural log of x minus 2 is equal to 3. All right, so now we have some nested logarithms, so this is a little exciting. So for the restrictions on this first value, x must be greater than 2. And for this interior logarithm, we have that 5 plus the natural log of x minus 2. This thing must be greater than 0, right? So let's solve this little baby inequality here. So let's subtract 5 from both sides. So we have the natural log of x minus 2 must be greater than negative 5, which we know is sometimes true. We're going to exponentiate both sides by e, so x minus 2 must be greater than e to the minus fifth. And then I'm going to add 2 to both sides. So x must be greater than 2 plus e to the minus 5. Right? So we have that x must be greater than 2 plus e to the fifth. We also have that x must be greater than 2. And then we just take the intersection of these two intervals, which is clearly this inequality here. So our restriction for our particular values of x is going to be that x must be greater than 2 plus e to the minus 5. Right? So let's just keep that in mind before we go through the process of solving this equation. Okay? All right, so let's get back to the star of this problem. So we have the natural log of 5 plus the natural log of x minus 2 is equal to 3. So I'm going to begin by getting rid of the natural log on the outside, so I'm going to exponentiate both sides by e to get rid of that. So that's going to give me 5 plus the natural log of x minus 2 must be equal to e cubed. Then I'm going to subtract 5, so I'm going to have the natural log of x minus 2 is going to be equal to minus 5 plus e cubed. Now I'm going to focus on getting rid of this natural log, so I'm going to exponentiate both sides by e. So that's going to give us what? It's going to give us x minus 2 is equal to e to the minus 5 plus e cubed, which is actually the same exact thing as writing e to the minus 5 times e to the e cubed. Right? So then I'm going to add 2 to both sides. So x must be equal to 2 plus e to the minus 5 e to the e cubed. So this is our possible solution, right? So now we need to check this with a restriction. So remember our restriction was that x must be greater than 2 plus e to the minus 5, right? So we need to ask ourselves, is this number that we have satisfying this inequality, right? So our question, 2 plus e to the minus 5 e cubed, is this greater than 2 plus e to the minus 5? So let's see if we can manipulate this question into an equivalent question for which we can trivially know the answer to. So I'm going to begin by subtracting both sides by 2. So I have e to the minus 5 e cubed. Is this greater than e to the minus 5? And then I'm going to divide both sides by e to the minus 5. That's a positive number, so I don't need to flip my inequality signs. So then we have is e to the e cubed, is this greater than 1, right? So remember, what is the number e? So e is approximately equal to 2.718, right? So when we cube this number, that's going to be greater than 1, clearly. And then we have e to the power of something greater than 1, so 2.71828 cubed. So this is greater than 1. E is greater than 1, and that's going to be 1 is greater than 2.71828 cubed. And of course, that's going to be greater. That's equal to 1, right? So if that is the case, that means this number is greater than 1. That means this is true, right? So therefore what? So therefore, since that statement is true, that means our solution, I'm going to call x star, is going to be equal to 2 plus e to the minus 5 e to the power e cubed. And that is the solution to that nested logarithm equation, right? So that's just some practice on how to solve logarithmic equations using a variety of other techniques in between. Hope you enjoyed. As always, if you enjoyed, please like this video, consider leaving a comment, and if you enjoy the channel content, please subscribe. We publish several new topics every single week. Thank you.